Thank you very much, and I am thrilled to be among such luminaries today to talk about such an important topic. The format is a little bit different from most of the talks and panels because there's so much to understand in quantum cryptography. There's both the quantum part and the cryptography part. And so Whitfield Diffie has very kindly agreed to give a presentation to begin, and then we'll do our panel discussion, and then we'll have about 10 minutes for questions at the end. I do want to ask everybody to be brief because, as you know, we're starting a little bit late. The food here is really good, so we don't want to cut too much into the lunch. And with that, I'll introduce Whitfield Diffie, who is a name that many of you already know. Turing Award recipient for 2015 for his work with Martin Hellman on public key cryptography. And with that, I yield the floor. Go get him.
A number of years ago, another cryptographer named Matt Blaze gave a talk called All You Need to Know About Cryptography in an Hour. These people gave me half an hour. So now I need to find out, of course, I have buttons, I don't really know how, what do you know? Oh, okay. So, I mean, you probably all know what cryptography is. It's using secrets to change things from useful form to useless form and control who can change them back and forth according to who has the keys. And the interesting thing about it is I see two origins of modern cryptography. I mean, you know, yes, people encrypted things going back several thousand years earlier than that. But there are two places we know about where basically techniques you can still see in the advanced encryption standard were developed. And they're by Al-Kindi in Baghdad about 200 AH, 1200 years ago, and Alberti and others in Italy only 500 years ago. And basically, I'm not going to go through they discovered cryptanalytic things, ways of breaking systems. I won't touch on that, but what they discovered the same solution to the problem, which is they're called polyalphabetic ciphers, and it means you change the way you encrypt with every character that goes out. And basically involves two things in computer science terms, you know, some kind of arithmetic, modulo addition, for example, and indexed table lookups. And as I say, it's amazing. You look at the advanced encryption standard, you see those as basic elements. So the question that raises, of course, is, wait a moment, you're looking back 500 years, 1200 years, but so much of what you're going to discuss is about the 20th century. What took so long? And the short answer is basically you can't do these things very well without mechanical computing. You can do a certain amount of it, but you can't really get it to be satisfactory until you get mechanical aids to computing. Cryptography as a security technique has a few sort of basic characteristics. I call this the managerial view of cryptography. It frees you from guarding the message path, right? I mean, one perfectly reasonable thing to do, say within this campus, is that you have phone wires and you know how they run, and you are fairly, do things to be sure people can't put taps on them, and you decide that's adequate. If you open an office in Moscow, that option goes away. You want to do things that are mobile. You want to do things involving satellites. You need to be able to protect messages without having the ability or the need to audit the message path. One of the particular things you can do is pass things through the hands of opponents. So somebody presents credentials or something, and you believe that they're tamper-resistant enough that it doesn't matter where you got them from. And symmetric classical cryptography acts like an amplifier. It takes the security of the key, which is, a few hundred bits, something you can put in a table, put in a safe, write down somewhere, and amplifies that to become the security or insecurity of billions of bits of communicated data. Now, coming up to what might, more people might call modern, there are basically four big things that cause surges in cryptography within the past century or so. First is World War I. You have two elements. One, you have radio. Right? Radio just bypasses all the techniques of the diplomatic bag sort that were known in the 19th century. But fortunately, you also have improved machining, so you can do mechanical things, and you have electricity, so you can do electromechanical things. And that dominates, that starts a big wave of work that runs through into World War II. World War II, what's new is electronics, things made of tubes, things that can operate very quickly, and we'll mention a couple of those. And then, as you go on into the 60s, things that are electronic begin to look more like computers. Right? I mean, they have buses with several bits, and altogether you have something that looks like the standard single instruction fetch cycle that moves a word of data along and keeps doing things to it. And then finally, in the 80s and on, you have big transformations due to the fact you begin to see things from a software point of view. Almost everything prior to that was designed to do what you could do readily with the computing techniques that you had. And now suddenly we get into an environment where, you specify some mathematical technique you like, and you have very flexible tools for implementing it. So I was inspired by the confusion the other day between Turing machines and Enigma machines to show you this one. This is, as far as I know, the highest grade mechanical crypto system of World War II, and it is effectively, you could think of it as two Enigmas packed in one box. They aren't exactly Enigmas, they work a little differently, but that's the important point here is that that's two rotor machines in one package, and one of them manufactures the movements for the other one. So there's a description of rotor encryption. To put this in modern computer science terms, it's a sequence of index table lookups, right? Now, they put the tables onto round objects, could be rotated. They did the indexing by rotating the objects. But what happens there is you get a character comes in, gets looked up in 3 different tables, it goes out, and then the indexes change, the rotors move. So that dominated what I'll call early mid-century cryptography, and ran on. Those things were still in use in the 60s and 70s. Undoubtedly, some are still in use today, but they're not widespread any longer. I want to say one moment, there's a system that I think represents one of the greatest discoveries in 20th century cryptography, but they didn't build a very good crypto system out of it, so it has a bad name. The US name for it is Purple. Japanese called it System B or Type 97 or various things. And the critical thing about it is that it's not made of rotors. Rotors are only of interest to cryptographers. They have all the problems of distributor caps. They get shorts because carbonization, things like that. And there was something else around in the world, and the Japanese thought to use it. And that is telephone stepping switches. People knew how to build central offices with tens of thousands of telephone stepping switches that behaved reliably. What would you expect? Very much greater reliability if you have a dozen or 2 dozen or 3 dozen of them. And there's a picture of the only piece of such a machine that I know of that survived, that came into the US possession. I am not aware of any claim that the Japanese had any left either. But they used 14, I think, stepping switches in their machine. If they had used 50, which is a perfectly feasible thing to do, I'm not at all sure you'd be reading that traffic today. Okay, taking a big step. There's the world's first digital telephone. happens to be a secure telephone, but that's only a tiny fraction of the operation. That thing, and in some ways that looks amazingly like a modern secure telephone, aside from occupying a room rather than fitting in your pocket. It does 2,400 bit per second linear predictive coding, all sorts of things that were well known in telephone technology later in the century. But that is the big inlet into post-World War II cryptographic work, because one, it showed you could have secure voice, and that led the way on to video and, instrument reporting and all sorts of things that were important. Okay. What characterizes the latter half of the 20th century in cryptography, one of the major things, is a transition from stream ciphers, things like those rotor machines that I showed you that encrypt one character at a time, to block ciphers that pick up, in the case of these things, either 64 or 128 bits and encrypt it all at once. And the reason that takes a while to come along is it turns on memory. And now memory, of course, is free, but it was pretty expensive at mid-century. However, there are things you can do with block systems. It started out with what's called identification friend or foe, sending a challenge to an aircraft that encrypts it in such a way as to tell a fire control radar, hey, don't shoot at me, I'm one of your friends, I know the same keys. And they didn't see any way of doing that just with stream ciphers. Now, that brings us to a lot of what this is about, which is, okay, we've discussed one side of cryptography, which is encrypting and decrypting messages. The other side of it, the thing was, well, you use keys to control messages. You amplify the security of keys, etc. Well, how do you get the keys? And that actually involves a great deal of the money, a great deal of the complexity. You have to produce the keys, you have to have inventories of them, you have to keep them in your safes, you have to be careful to know whether, get them to where you want them to go, use them, and finally destroy them. So that's a big part of any large-scale crypto-secure operation. And, what got me invited here is work done in the 70s on saying, well, wait a moment, can we alter the cryptography in such a way as to make it easier to manage the keys? And what resulted is called public key cryptography. You encrypt and decryption. You manage to arrange that not everything is secret. You have public pieces of information that are cognate to secret pieces of information. And this gives you two basic phenomena. One is key negotiation. You and I want to arrange a key between the two of us, and it turns out that by exchanging a sequence of messages, we can do that much more economically than shipping a key from one of us to the other. The other thing it gives you is a phenomenon called digital signature, which in some sense has made internet commerce possible. So it wanted to behave like a written Unterschrift. You transform the message in such a way that only you could do that, but many people can recognize what you did. So many people can recognize your signature, but only one person can produce the signature. There are three sorts of things that emerged early on and are still in use. Vest, Shamir, and Edelman system. We have Shamir here. We couldn't get the other two. Diffie-Hellman key negotiation. You got me. You didn't get Marty. And El-Gamal signatures. We don't have any sign of him. And they all turn on some things that are going to become important to this discussion in a moment. Now, in some respects, they were succeeded by a phenomenon called elliptic curve cryptography. For the first time, we get the mathematics involved up into the 19th century. And it was invented by two charmingly different characters named Neil Koblitz and Victor Miller. Victor Miller was working for IBM, and he went from there to effectively working for NSA. Neil Koblitz was and remains a communist and close ties to Vietnamese mathematicians and so forth. So two people on different sides of the political spectrum came up with the same thing. And basically, you get phenomena called elliptic curve Diffie-Hellman or elliptic curve El-Gamal. RSA has special characteristics, and basically nobody's yet discovered. You can do it in ways different from the original integer arithmetic way, but you don't get any better results. So, humph. Ah, there we go. Slides not in the optimal order. The way the system's called RSA works is that you're doing exponentiation over a modulus that is a product of prime numbers. And the result is that you have two different exponents called reasonably encrypting and decrypting exponent. And if you know the encrypting exponent and know the modulus, you can't figure out the decrypting exponent. You really need to know the factors in order to do that. So the factors are the big secret, or one form of the big secret. So let's go back a few. Okay. So this depends on several things. Fact is, so to speak, multiplication is easy. Exponentiation is easy. Exponentiation is particularly easy because it occurs in a time that's the log of the exponential. And finding primes is, sort of easy. It certainly is perfectly feasible. Factoring by comparison with any of those things is very difficult. So all of this turns on the ease of some problems and the difficulty of others. Just in brief, what happened with public key is a shift. Cryptomathematics was largely concerned for a good part of the 20th century about correlation, figuring out relationships between messages, figuring out how much sequences looked like linear sequences, various things like that. And what changed, oh, okay, that's still on, yeah, that's just an assortment there of the mainstays of classical cryptomathematics. Once you got to public key, we had a lot of use of number theory, and suddenly a whole lot of people began working on factoring and discrete logarithms, which are the two problems underlying the main cryptographic systems in use. Okay, so I said that the secret thing in RSA was the factors. Right? You could put that another way. What you actually use is a number called phi, which tells you the number of invertible elements in a finite ring, and that number is p minus 1 times q minus 1. And it's the length of a cycle. And that's why what comes up in quantum computing is that finding cycle lengths turns out to ruin. If you have a way of doing that, you can ruin the system. So note this differs. If you're intercepting classical traffic, you don't know how to do anything with it. But if you're intercepting public key traffic, typically you know how to do something with it. You know how to encrypt. So you could generate a lot of things and see whether you match what you're seeing, or you could continue encrypting things and see what sort of cycles they get into, a whole lot of things. And what's hard here is you can go forward easily, you don't know how to go back. So this is very much like being on a racetrack, right? You get 5 points if you can tell me which racetrack that is. You can go around, and in some sense, if each step is an encryption, right, the place you want it to be is just right behind where you are. But of course, going backwards on a racetrack is not a good idea. You probably get run over. But here we have an interesting case, because this exponentiation has a cost that's logarithmic. So if you want to go 1 billion times around the track, it's not free, but it only costs 30 times as much as going once around the track. So roughly speaking, you can go as far along the track as you like, but you might be in a little bit of trouble because where are you, right? And if you could figure out the length of the track, then you could get back, you could get to the places you wanted to be very quickly. But the big secret is the length of the track. Right? And so you're in a situation like, now, those are lines of latitude, and if you don't know which one you're on, then you don't know how to get around the world. So the critical point is that just in the 90s, Shor discovered a technique for using quantum computing to find cycle lengths. And that is why everybody is worried that the systems I've been describing are going to be broken. That once you know the cycle length, you know how far to go, you can do the exponentiation, etc. A sort of quick description of quantum computing is it comes at superly parallel. It's not quite like, well, an undeterministic polynomial time or something, but it runs lots of things, lots and lots of states simultaneously. The physicists have been promising it to us for 30 years. Judge that either way you like. Sarcastic people think it's like controlled fusion, and optimists think it's around the corner. There has been a lot of money invested in it, and the worry about it, incidentally, it has lots of things it will do independent of cryptography that seem to make it worthwhile, whatever happens to cryptography, right? And maybe it'll solve protein folding problems and revolutionize biology. But our current crypto will suffer from it. The key piece of jargon is a qubit, right? A classical bit is a 0 or a 1. A qubit is a probability distribution. And you have a whole lot of, something starts and all of these qubits are in unknown states, and after a while they settle down somewhere and you have the answer. And it's jargon is, keeping the whole thing coherent, things like that. I have no insight into how quickly this is going to happen, but the big money seems to believe in it. So, wager your money where you like. Now, I want to just take 1 second to mention something else, because there are two things with very similar names and some similarity of concept. Namely, they both have to do with quantum mechanics. But the other one used to be called quantum cryptography, and was invented by Stephen Wiesner, son of a much more famous father who was science advisor to Eisenhower and president of MIT. And it uses quantum phenomena. These days, its current form is to negotiate keys. And Chinese have done a lot with it and ran it over satellite channels. And somebody not far from here ran it over 30 kilometers, I think it was, of optical fiber. But all the optical fiber was wound around a big drum in the office. So, as a result of this, NIST, National Institute for Standards and Technology in the US, has had a project running for several years to develop what are called post-quantum crypto systems. And on the 5th of July this year, it issued several new standards. One for key negotiation, and 3 for signature. They also announced that several things that they've been running a contest. And so it started out with, I think, 59 submissions, and they got it down to 26, and then they got it down to around 15, which is the way they developed the advanced encryption standards. It's a process we have some evidence works well. And even that left 4 things were not yet standardized, but were held over for further study. One of them didn't last very long. End of the same month, it was announced, and certainly claimed, that people at KU Leuven Is that right? Yeah. Okay. Had broken it with nothing to do with quantum computing. They had, you know, a PC. Now, looking at another institution with an interest in the subject, the U.S. National Security Agency, basically, look, there's been a transition, say, since World War II, from cryptographic systems being a competitive advantage. If your systems were better than your opponents, they couldn't read your traffic. If you were good at reading traffic, you could read theirs. And, you know, the people, I can't judge, but lots of people like to claim the war would have been this, that, or the other much longer if that had gone differently. Basically, these things have evolved into standards. They're common ground for whatever you're doing. And so in 2005, the National Security Agency announced a set of public cryptographic algorithms that it was going to trust for all levels of secret information, loosely speaking. They had some holdouts on it, but that's, you know, if you employ an algorithm development group, you have to deploy its products, or it loses morale, and that may be the good part of the reason. And so those things in fact became standard, and we could, at that point, cryptographers might reasonably have thought, okay, we solved our piece of the problem, you guys can go work on, you know, flaky apps and network protocols and things of that kind. We're going to retire. Then quantum computing reared its pretty head, and in 2015, NSA issued, I think, as impolitic a statement as I can ever imagine, because they had been jawboning and leaning on all the people in NATO and other alliances to adopt what they were calling Suite B. Okay? And suddenly they issued this thing and said, well, if you implemented Suite B, thank you, but if you didn't, maybe you shouldn't bother, because we're going to come out with quantum-resistant algorithms in its place. Nothing happened for 7 years, and then this year, or just a few days ago, they announced they've changed its name. Their marketing has improved a little. They now call it, the Commercial National Security Algorithm Suite, and this one is Suite 2.0, and they have introduced 2 new public key type systems, and we're discussing those, and carried over symmetric things, and then fascinatingly introduced a bunch of Merkle signature sort of things that are popular with the cryptocurrency people. So with that, we got to arguing about these things. So I've now said, I hope, everything that isn't controversial.
Thank you. That was concise and educational. And now, as you say, it's time to fight.
Right.
And I bring up the combatants. Actually, it's not going to be a fight. We already did our fighting. Now we all agree. And we'll start off with somebody who you all know, Vinton Cerf. He is, of course, an ACM A.M. Turing Award recipient in 2004 with Robert Kahn for his work in TCP/IP and Internet evangelism. And he is sometimes called father of the Internet, Vinton Cerf. Whitfield Diffie, of course, needs no further introduction. Third up, we have Adi Shamir, who, as you know, is the S in RSA. He received his Turing Award in 2002, together with Ron Rivest and Leonard Adelman, for the implementation of public key cryptography, although he may correct me on that a little bit. Okay, close enough, yes?
Yes.
Okay, good enough. Then I'm very pleased to have two people from IBM, the crypto group in Zurich, Switzerland, who came up with 3 of the 4 standards that NIST selected. That would be Vadim Lyubashevsky. He is a principal research scientist at IBM Zurich. And Gregor Seiler, who is, what is your title there? Research scientist, yes? Yeah. Okay, very good. You may applaud. We have 50 minutes for our talk, and then we'll have 10 minutes for questions. And I'd like to start out with the questions about what is it that makes crystals, which are 2 of your suites, yes? Let me know if I'm saying that right. And Falcon, what is it that makes them more hard against quantum computers, theoretically?
Okay, so sure, I can answer this. So, I mean, since we had these standards, I've had IBM schedule a bunch of interviews for us, and this question always comes up. I mean, the main question is, how do you know that it's quantum resistant? So, and with cryptography, so then I say, okay, here's the thing, cryptography, the way we think something is secure, we have a mathematical problem, a lot of people work on this problem, and if they can't solve it, we think it's secure, and then we try to build cryptography on this. And then invariably says, okay, well, they seem a little concerned, but how do you prove, a quantum computer is so powerful, how can you prove that it's secure? And so I feel like the message is not getting across. So then I say, okay, let's forget about quantum computers and let's just talk about classical computers. Why do you think that factoring is secure, right? Because people have worked on it, and they can't solve it. But then I feel that there's a bit of a misconception between the public, why they think cryptography is hard. Maybe they think of factoring as like gravity, maybe people don't understand it, but it's there and it works. But I think that maybe 20 years ago or something, 30 years ago, people did just an informal survey at some theoretical conference. Do you think factoring is secure? Do you think it'll be broken? And I think about 30 to 50% said, yeah, we think it might be. There's a good chance it'll be broken. Now, I don't think that's a fear that people have with gravity, right? So I don't think 30% think it'll be turned off. So this is, I think we've been sort of living in a bit of an ignorant bliss, thinking, oh, everything works, so, no problems. And, we can just continue living in the same bliss, but now with post-quantum cryptography. I mean, we worked on these problems. We think they're hard. This is the best we can do. One can't expect anything more. And, we just have to hope that we pick the right algorithmic problem. So, and if you ask, like, why, I can come up with some answers, or, I can, point to which racetrack. There's no racetrack with lattices. I don't know. But it's really, the answer is that people have tried to solve these problems for about 30 years. Quantum, I don't know. But classically, I think people are fairly sure of lattice cryptography, and the NSA has done a lot of work on their part, I'm pretty sure. And so this is why we are sort of confident with.
Let me add something to that. We have, loosely speaking, failed so far to develop a complexity theory that gives us real confidence in cryptography. But if you look historically, right, World War II, everybody was very taken with the fact that a whole bunch of things believed to be high-grade systems were broken in World War II. But if you look at the history of cryptography since then, in NATO in particular, you have lifetimes for crypto systems that runs into the decades. So that's the basic phenomenon we have for knowing things are secure, is that a lot of people have tried over a period of time to break them without success.
I have a slightly different take. I think that I agree that we don't have a theory. The way I think about why people are using RSA is because the best thing which was available until the competition for post-quantum cryptography. Why are we going to use the lithium and Kyber and your inventions based on lattices? Because it's the best available schemes which seem to be the most secure. I wish we had even better reasons to choose it. But the alternative is simply not to use cryptography, not to use public key cryptography, and we cannot go this way. So I wholeheartedly agree that NIST should have run the competition. I think that many of the less secure schemes had already been found to be less secure. I'm a bit concerned by the fact that almost all the remaining schemes are based on lattices. So we are putting, in some sense, all the eggs in the same basket. But that's the best we have.
I see Vint knitting his brows.
Well, the vocabulary that we use, I think, is potentially misleading. We say secure. The real heart of all this is how hard is it to break? It's called work factor. And I think the real issue here is, do we have a scheme which is sufficiently hard that it will take too long for someone to usefully break the algorithm and get access to the information. The thing that's a little scary about all this stuff is that if you find an algorithm which is hard to break at time t, at some time t in the future, it may be less difficult because we have better computing capability, whether it's conventional or quantum. But the heart, I think we should not be so comfortable with the word secure. We should just recognize that it's a relative work factor that postpones the breaking long enough that the information is no longer useful.
And in the lead up to this discussion, I heard a few different terms being thrown out. I think you said quantum resistant. What are some of the words that you hear?
Post-quantum, quantum safe.
Post-quantum, yeah.
Quantum safe is a problem because it indicates that we're pretty sure that it will not be broken. It's safe.
The vocabulary could be improved.
Yes, yes. So this is something that I know that nobody really likes to put their money on. But can we talk about a timeline for when you think post-quantum cryptography will be needed? And I know that none of you are quantum engineers or anything like that.
No.
You should ask us for a hand vote. Ask how many of us think that there will be a quantum computer capable of breaking RSA within 10 years, for example.
All right,
Then
let's do that. Go for it. In 10 years. Let's see it in the audience, too, because some of you are quantum people, right? How many people think it'll be within 10 years? 20 years.
Yeah, that's probably very likely.
30 years.
Maybe.
Take the time, we'll be dead, we won't be answering, we'll talk about it.
Well, okay, so we should record this and then we'll see.
Between 10 and 20 years seems to be the threshold.
Yes, at the 50th HLF, this will all be coming up again.
So, my company has spent some money on this at Google, and I can tell you that we made some progress. We use a cryogenic system. We have at least two sets of quantum computers, one with 53 qubits and one with 72. But what I've learned in my paper-thin knowledge is that maintaining the coherence of the qubits is pretty important. If you can't maintain the coherence long enough, then you can't complete a computation that's useful. So how do you deal with the loss of coherence? And one answer is, well, instead of just using one physical qubit to do a computation, why don't you use a collection of qubits in order to do what's called error correction? So you have multiple physical qubits to represent a logical qubit. And the lead in the project told me that you could imagine the possibility of 1,000 physical qubits needed to maintain one logical qubit long enough to do something useful. But then you might need more than one logical qubit to solve an interesting problem. So if you needed 1,000 logical qubits, you might need 1,000,000 physical qubits. And it turns out to be hard to build a 1,000,000 physical qubit machine. So that leads you to the next possibility, which is, well, maybe you could build a quantum computer with a certain number of physical qubits, say 1,000 just for the sake of argument, and then you could make 1,000 of those machines. Now you have another problem, which is how do you hook them together in a useful way, and that's why you hear people talk about quantum networking and quantum internet, where you basically try to entangle the machines that have the physical qubits by sending entangled photons around in this quantum network in order to entangle the computers so that when they're running, they are concurrently doing a useful calculation. So in terms of your earlier question about when will we have a functioning, useful quantum computer, I think we're a long ways away from being able to do something seriously useful. And most of the seriously useful things, apart from Shor's algorithm, tend to be solutions to optimization problems, for example, which are of real interest. I mean, if you can solve the traveling salesman problem in a reasonable amount of time, you could usefully apply the machines. So at this stage of the game, we're some years, to say possibly a decade or more, away from machines that can be usefully applied. At least that's where I sit.
I can add to this my personal threshold for starting to believe seriously that quantum computers are going to become a reality. According to the IBM white paper, which was published several years ago, by the end of 2023, they should have more than 1,000 qubit machine.
Really?
And if this happens, I think that we'll be able to play with it, implement error correction, which we cannot do with today's 53 qubit devices. So I think that if IBM will manage to stick to their predictions and create a usable, fully usable 1,000 qubit machine by the end of next year, I'm going to become a believer.
I do want to mention, for those of you who don't know, that when we talk about numbers like 40 qubit, you think, wait a second, there's billions and trillions of bits on my computer. Each qubit actually doubles the power, correct? Is that accurate to say?
Not exactly, but
okay, but
yes.
it is an exponential thing,
The number of states that you can represent with a qubit goes up rapidly, by powers of 2 relative to the binary.
But the one usual standard misconception about quantum computers is that they don't run 2 to the n computations in parallel, searching for a solution. It's more complicated than that.
Yeah. It looked like you were about to say something, Gregor.
Yes, I wanted to add something basically about what was said before about the hardness assumptions that we are using in quantum-safe cryptography. So I think we don't have to necessarily give up the hardness of the classical schemes like basically factoring-based schemes and discrete log, because it's always possible to combine several schemes in a way that as soon as one of the schemes that are used is secure, or the underlying assumption is hard, the resulting combined scheme is hard. So we can essentially add quantum security to the schemes that we are using now.
This is related to an interesting question which might bother companies and individual users. Should they be worried about using today's algorithms in case it will be broken by that potential future quantum computer? So I believe that companies should definitely, companies which are producing systems, communication systems, and providing security should definitely be worried and should definitely include the newly developed post-quantum algorithms. But for users of cryptography, I think that the danger is not so big for the following reason. First of all, since we all seem to agree that large enough quantum computers will not be available in the next 10 to 20 years, the real danger is that somebody is going to record the cipher texts which are being used today. They will not be able to break them because we don't have at the moment large enough quantum computers, but in 20 years' time, they will be able to use the future quantum computers in order to look back and solve those problems in the past. So anyone who has long-term secrets which have to be maintained over tens of years or hundreds of years, I'm talking about governments, I'm talking about spies, I'm talking about very high-level secrets, they should be worried, and they should probably switch right now to those hybrid approaches that you mentioned.
Okay, and Vint has something to say on that.
There is a counter-argument. I don't disagree with what you just said, so it's not to disagree. But I will point out that all of the arguments about the weakness of algorithms that can be broken by quantum doesn't necessarily break the cryptography that's used to encrypt the information. So if you didn't use public key crypto or RSA or some of the other algorithms to do key distribution, if you just use the symmetric keys of sufficient size, you may have information that is adequately protected for fairly long periods of time. So the weakness here has more to do with the key distribution than it does with the actual encryption algorithm itself.
So you're basically saying that for the highest level secrets, don't use public key cryptography at all, and then you are safe.
Yes. I also think a brick is safe, you know, it just sits there and it doesn't do anything. It's very secure.
Yeah.
Gregor?
Yeah, so I fully agree that these store now, decrypt later attacks are probably the best argument for switching to quantum safe cryptography now, or basically using these hybrid schemes. But I think there's also other very good reasons why, even if someone doesn't basically encrypt data that needs to be secure for a very long time, they should make the switch now, because there's basically, it takes a very long time to deploy cryptography in large systems, like, for example, the internet. So standards have to be changed and people have to be trained. We need to also understand how these new schemes can be implemented in practice in a secure way. So there's this large topic, for example, of side channel attacks, where if you, for example, can measure the power consumption of the device, you can infer something about the secret key. And this is something that is really only at its infancy in basically related to these quantum safe algorithms. So all these things need to be developed before we really have secure solutions in this area, and this takes a very long time. And so I think even if basically the quantum computer is now out in a very long time in the future, it might be too late if we wait until basically the threat becomes more.
But that's exactly
Wait a second, I think Vadim had something to add there.
Oh yeah, just adding to, I think maybe the world is also becoming a bit more complicated. There's all these distributed systems, for example, are now existing. So, I mean, just take Bitcoin. I mean, whatever value you assign to it. Now, for example, once you switch, or something like Bitcoin, blockchain related, where everyone is in charge of their own key, so you won't have Google or IBM, for example, saying, okay, we're going to change our browser and now everything is fine. Everyone has to go in by themselves and do this switch, and if they don't, it all collapses. So, and that could actually take quite some time. Now, I think we are going in the direction of more distributed, more people will be responsible for their own data because they don't trust anyone else with it. And so this is why at least it's worth seeing whether at least it can be done, because we know that, you know, Kyber, dilithium for the internet, I think it's fine. For other things, you need a bit more cryptography that's not just encryption and signatures, and that has, you know, that's still in its research, in the research domain. And we kind of have to hurry up if we hope to have this distributed computing together with cryptography in the future.
So there's a wonderful corollary to what you just said. If you're doing the design of computer communication protocols, one of the things this conversation should convince you of is that you better design those protocols so that they can change the algorithms that are used for security. And so you need to anticipate that there will be changes, that you will have to replace older algorithms with new ones. So the design of the protocols have to be prepared for that case. If you don't do that, then you're really stuck in a bad place.
So exactly for this reason, I recommended that providers of communication systems should build systems now which have a switch. You can put the switch in the RSA or other factoring discrete log-based schemes, and you could turn the switch to the other lattice-based schemes, the newer ones. So I'm all in favor of having this switch. The question is whether you, as somebody who has a secret that will be irrelevant in a year's time, whether you should already turn the switch to the new algorithms, or you can continue to use the current suite of algorithms.
Well, there's a problem with that particular model of throw the switch. This gets to your distributed computing situation. When you're communicating with a collection of people who have a mixed implementation of cryptography, you may need to negotiate to figure out whether you can even throw the switch for that particular target, because they may not be ready for that.
You were going to say something, but I think it was a change in topic a little
sure.
bit.
Well, since you pushed me in now, I'll come in now. There's a lot of talk about the scaling problems of quantum computing. Now, the scalability of RSA is substantial. So I'm curious if Adi has an instinct for, whether you can't, in that part of that memo I showed from 2015 from NSA, one of the things it said was, okay, jack up your RSA keys from 2,000 to 3,000 bits. Well, 2,000 to 4,000 bits is common now. You can do 16, 32. Daniel Bernstein is playing with a modulus of 1 billion bits just to show you can do it. So my question is, what's your judgment about whether RSA can just steadily outrun things maintaining a 100-year lifetime or something?
Okay, if you have a secret that you want to maintain for 100 years, please don't use RSA.
He doesn't
It comes from me.
sued. That's the thing.
Isn't this like the K-Pro problem, where you're selling the next one and then you yeah.
This reminds me of something which just came up. You know that it was traditionally very hard to make money out of cryptanalysis. People who made cryptographic machines made money, but those who broke them usually did not. And yesterday it was announced that Peter Shor, the guy who broke RSA, got his share of a $3 million breakthrough prize, which is one of the most prestigious prizes for breaking RSA.
Yes.
So congratulations to him.
Yeah,
Somebody's And with that, actually, I would like to switch topics quite a bit.
Okay.
We still have some time, but I want to make sure that we get plenty of time on this. Since we are with so many young researchers, what might young researchers look at now if they want to get into quantum cryptography? What open source projects or research subjects or anything like that? And I know that you folks have Qiskit, if you want to talk about that.
Yeah, so maybe I say something first about quantum safe cryptography and not quantum computing so much. So, yeah, so in this area, I think we have pretty good schemes now for the basic tasks like encryption and digital signatures. But on the other hand, if it comes to more advanced cryptography, so cryptography nowadays really is not just these basic tasks, but many more advanced protocols. And in this area, the research is basically very much behind what one can do in the pre-quantum world. So basically the post-quantum candidates or quantum safe candidates for advanced cryptography is still lacking, and there's a lot to be done and also interesting research going on. So for example, I think about zero knowledge proof systems, for example. And this is a very interesting topic right now to work on.
I'm sorry, I didn't mean to break in to the topic. Was anybody else going to add on to that before?
Well, I'm just thinking a little bit, it's not my field, but you can imagine that since we don't yet have fully functioning quantum computers to try out some of these ideas, but we do have the ability to simulate the quantum computers. And I've been fairly amazed at what computations you can do simulating this on a classical machine. So there are programming languages that we use at Google, I imagine IBM and others have similar capabilities, so some research could be done on just looking for new ways of using quantum computing to solve hard problems. That's not an unreasonable dissertation topic.
Actually, simulating a quantum computer on a classical one is not easy at all. You can hardly simulate the Google's 53-qubit device, and this was actually used in the quantum supremacy. They had to verify the computation, and therefore they could barely do it with their 53-qubit machine. And if you will take a 100-qubit machine, and I'm not sure that the same kind of demonstration will be verifiable, because we don't know how to simulate a 100-qubit machine.
Yes.
Yeah, so just sort of to answer your question about what can young people do in quantum-safe crypto. So in addition to what Gregor said, so you can design more schemes, but that's if you're a cryptographer and you don't even need to know anything about quantum if you want to just work on designing cryptographic schemes. But there's so many other areas you can do. For example, if you're more into mathematics, cryptanalysis. So you don't need a lot of mathematics to design schemes, but you need quite a bit of mathematics to break them. And of course, if you want to go one step further, now you have to learn quantum and you do quantum cryptanalysis, which is kind of the whole, raison d'etre for this whole project, is to have a quantum-safe algorithm, quantum-safe cryptography. And I mean, honestly, I don't think there were just enough people yet who have worked on quantum-safe, quantum algorithms, quantum attacks, to sort of say, oh yeah, nothing can be done. But it is the best we have. Kind of interestingly, actually, the way these schemes came about was, 15 years ago, one of the pioneers of this, Oded Regev, was actually trying to solve a quantum problem, and he could, using quantum algorithms, he couldn't, and then he kind of came up with cryptography. So he was partially happy. But really, his goal was to to come up with a new quantum algorithm for something.
Yeah.
So if you want to develop new cryptographic schemes, the best advice is for you to stay away from lattice-based scheme, because we have sufficiently many good examples at the moment. What we really lack are entirely different ideas which will turn out to be secure, because at the moment most of the approaches which were not based on lattices and which were proposed to NIST had been broken very badly. So any great new idea for a new basis for public key cryptography, which is not using lattices, will be greatly appreciated. Now, if you are the breaking guys and girls, then the best advice I'm going to give you is to try to find quantum attacks on the lattice-based schemes. This will make a huge difference and big impact.
I know it sounds like I'm asking you to give us the keys to the kingdom, which may not even exist, but you say look for something other than lattice-based cryptography. Do you have some sense of what that other thing may be?
So people had a variety of approaches. For example, people were using the difficulty of solving systems of algebraic equations. This is an area that I personally worked on, breaking it classically. I broke the scheme which was called balanced oil and vinegar. So we didn't know how to break extensions of this scheme, which is called unbalanced oil and vinegar. This became one of the submissions to the NIST competition called Rainbow. Unfortunately, that scheme was broken a few months ago. So the scheme which was broken a few weeks ago is based on isogeny of supersingular elliptic curves. You don't have to understand anything about it, but almost all our attempts to base public key cryptography on a totally different basis have failed so far, so I cannot tell you what will be the next big idea there.
Is there any mileage out of Diophantine equations for this?
Yes, except that it's very hard to... Diophantine equations are those equations which are solved by integers, but of arbitrary size. And while there are many difficult problems there, it's very hard to control how big are the solutions. Yeah. So they may be so big that you cannot even write them down, and therefore they cannot be used as a key or as a...
It's very secure. No one can even write the key. Okay.
So my intuition runs in another direction, which is there is a phenomenon called cellular automata. Mm-hmm. And cellular automata, there are invertible nonlinear cellular automata. They're rather hard to find. And they're unlike the usual mechanisms used to build things like AES, in which you've built it explicitly so you exactly know how to invert it. Right? a bijective cellular automaton needn't be obviously invertible.
That's
so I think
interesting.
my intuition now doesn't run any, I'm not going to tell you how you should use this, but I think it's an area in which you might find something.
Interesting.
You heard it here first. Everybody run out and claim your Turing Award or your Fields Medal.
Maybe we should also talk about where you can learn about this field if you are a total newcomer. So
Please.
it had already been mentioned that Qiskit is a resource which is produced and put online by IBM. Maybe you want to say a bit more, but I highly recommend that all of you should go to Qiskit, K-I-S, Q-I-T.
QIS.
QIS, sorry, QIS, K-I-T, and .org, and they have a wonderful introduction, gentle introduction to the field, many worked out examples of how quantum algorithms operate, and another great resource for more advanced people are the lecture notes that Scott Aronson from the University of Texas in Austin had put up on his webpage. So this is an undergraduate course in quantum computing, and you can download both the elementary version and the advanced course from his website.
Thank you. Thank you. No? Would you like to turn it to questions, or is there anything that you feel we should have covered that we haven't covered?
Oh, there is
please.
one other thing that you guys can help me with. There's a guy named Jack Hidary who's written a book on quantum computation, if I remember correctly, and it's got a second edition. I just got a copy, and I was very impressed by how clear the presentation was, but I'm a newbie at this. Is that also a good reference, or do you not know?
I don't know it,
Okay, so
not comment.
who knows?
But maybe I should mention one other open problem, big open problem, which is not directly related to cryptography and cryptanalysis, and this is developing completely new types of algorithms for quantum computers. If you look, from high above, we basically have two very clever and innovative algorithms. We have the Shor's algorithm for factoring and computing discrete logs, which is quite specialized. And we have a general algorithm, which is called Grover's algorithm, which can find a solution among 2 to the n possible candidates in square root of 2 to the n time. And from a very high level, these are the only real algorithms we have developed, and most other algorithms are kind of variants. So coming up with something else which gives you a huge advantage when run on a quantum computer compared to a classical computer will be a major advance of the field.
So can I ask another naive question? There's another kind of machine that was referred to as quantum, but created great controversy. It's the D-wave machine, which is an adiabatic design. My question is whether its computational ability is of any use at all against cryptography that we've been talking about. I don't know
Maybe
the
you want
answer
to
to that.
answer?
No, in the community they believe not, because it's more of an annealing type thing that does not really use the fact that you can put qubits in superposition and they all cannot really interact together. So I think the general consensus is no, we're waiting for a fully fault-tolerant quantum machine if we're going to break cryptography.
Got it.
I've seen comments by very reputable sources saying that they're not convinced that there's anything quantum which is really going on in their machines.
In those machines, yes,
Yeah,
I know. There was a huge controversy about that, yes. Okay, questions?
Oh, and I should mention that, again, you can use these simulators right now, and if you're used to classical computing, you will have to change your thinking quite a bit to understand quantum gates. Even down to the gate level, everything is different.
Maybe if I can mention another direction, because Adi was saying we only know 2 quantum algorithms, so this is important if you want to break cryptography. But if you want to build cryptography, I want to say that now the new schemes, they're based on a completely different mathematical notion. They're still classical, but they really, if you work they look like Diffie-Hellman. So the encryption scheme has the same principles, intuition, as you had 40 years ago with Diffie-Hellman. The signatures have the same idea as you had maybe with RSA signatures or Schnorr signatures also 40 years ago. So the interesting thing is, despite all this progress and different things, the basics, we're still doing it the exact same way, just with different structures. So maybe a less ambitious thing than trying to find new math, on which is hard, is maybe come up with a slightly different thing that at least we thought we had something different with lattices. But then if you work hard, it becomes Diffie-Hellman. And then that's when people actually liked it, because people like the things that are saying, okay, now it looks like Diffie-Hellman, we get it, let's use it. But to come up with something brand new, and maybe that's how you will come up with some new math. But now we're really trying to come up, if you want to do encryption, you do it this way. If you want to do signatures, you do it this way. We don't have really any new approaches, let's say. So maybe that is also an interesting, maybe less ambitious problem, but it still seems hard. Because
And I'm sorry, where did you see this? The thing that reminded you of Diffie-Hellman?
So schemes, Christmas Kyber is really Diffie-Hellman using different mathematical structure. But the concept of how you exchange keys is very similar, just different algebra.
Interesting. Shall we take questions?
Sure.
All right. So somebody out there has a microphone. Could you hold your hand up so we know where the microphone is?
I thought they had a padded ball.
It's over there. Oh.
Yeah,
What happened to the rubber cube?
Punt kick it into the stands.
They only had 6 lavalier mics, and they use a lavalier mic in that. So they have to have a runner going around with the microphone.
We stole the 6th one.
We stole the 6th one. I could just take this off.
It's our fault. So it's not as much fun
Throw you my lavalier.
to ask questions. Yeah. Well,
We do
that's a
have
possibility.
a microphone over there, and I believe that's our first question.
Hi, thank you very much for really great insights. I have one question to Adi and to as well. So earlier in this, we had a panel discussion on AI, and there was 2 elements which came up: science AI and engineering AI. So I come from engineering background, so I wanted to ask you, what are the solutions you think could come from the engineering point of view? The maths part of cryptography is quite clear. We see that the mathematics of RSA, but what could the engineers do? What are the frontiers for engineers? So that's my main question. On the related note, I have one question to Vincent. When we had a early discussion on the internet security, you mentioned the next frontier could come from hardware software co-integration, and you gave one example of Cherry project. But this approach, how feasible it is for the quantum, as during the discussion it was pointed out that it will take years, 2 decades, for quantum machine to be even accessible for the developers around the world. So, your thoughts?
I'm not sure I could hear there is some kind of echo in the room.
It's really hard to hear that.
So none of us could really
I'm glad
understand
I'm
the
the only
language.
one that was having
If I
trouble with
understand,
that.
you're asking about quantum applications to AI, and then there was a second part to that?
Okay,
or-
I will just repeat my question. So I just wanted to ask, this 2 parts, science part and the engineering part. So I was asking, what are the solutions or advancements which you think could come in the crypto direction from the engineering point of view? Because a lot of developers, they did not from a mathematics background. I myself, I'm more like an engineer.
Okay.
I think I got
I
it.
had a question to Vincent, because one of the things you mentioned Cherry project and the hardware software co-integration, the next frontier of security. But the quantum hardware, as you pointed yourself, people from IBM, that it will take maybe 10 or 20 years to be available to the other people, like outside the company's laboratory. So this approach of hardware software integration, how would it work for the post-quantum security from
So-
point of view?
So if I could just restate that, as I understand it, I'm going to just take the first part to start with so that we don't get too complicated. If I understand, you're dividing the science, that is how quantum works, and the engineering, how it's implemented. Is that accurate, more or less?
Yes.
So I can answer the engineering side. I've been following many publications about a variety of ways how to build quantum computers. The classical one is the superconducting cryogenic kind of system. This is the one which is being used by Google, for example, and by IBM, and it had been proven successful with limited number of qubits, and let's wait and see how it evolves. Now there is a different approach that Microsoft had bet on over the last 10 plus years, and this is the topological qubit, which is based on Majorana quasi-particles. Now we don't have to understand the physics, but there is a certain phenomenon, and Microsoft decided to bet on this technology because it is going to be much harder to influence those qubits. They are inherently more stable. The problem is that so far, after more than 10 years, Microsoft still hadn't demonstrated a single qubit based on the Majorana quasi-particles. They only recently published a paper showing that they exist, but it's still not usable as a qubit. So progress in Majorana, in topological qubits, is very slow, but promising in the sense that once you can build a small device, you can scale it up with much less it's not going to be so problematic to deal with the noise. And then there are other companies which are trying to use photonics. They are trying to entangle photons, and you're not going to have superconductors. There are techniques based on Rydberg atoms. There are techniques based on ions. So I can go on and on. There is no lack of approaches. The main one, the one which has been used the most, is the one based on cryogenic superconductors. Yeah. But this was a bit technical.
So I think, if I'm remembering correctly, Bell Labs is also experimenting with the topological quantum design. I seem to remember seeing some reports from about 5 years ago. I don't know what's happened recently.
Yeah, I just want to add, so certainly there are very big engineering problems in the construction of quantum computers, but then there are also interesting engineering problems on the non-quantum side when it comes to deploying quantum-safe cryptography. Because, for example, I mean, current smart cards that are, for example, used for credit cards, they have accelerators for big number arithmetic in order to do the RSA crypto system in an efficient way. And what we need to basically make this transition to quantum-safe cryptography is new types of hardware that is accelerating the new kinds of algorithms that we have. And there are interesting research problems around this.
But maybe to avoid confusion, because most people here are not experts on quantum technology, to encrypt data, to decrypt data, etc., you don't need a quantum computer at all. Even if you are using the post-quantum algorithms, they are described in a totally classical way, and you can use any available computer to do the encryption and the legitimate decryption when you have the key. It is only the guys in the basement, somewhere near Washington, D.C., or Moscow that have to use the quantum computers and have to understand them.
Shall we take the next question? Where do we have the microphone? Oh, it's already there.
And during it you mentioned short quantum hours or factoring hours. But my question is more about classical computational model. So how do you think, is it possible that in the nearest future people will come up with, say, polynomial algorithms for factoring hours? And here with polynomial I mean with respect to classical or genetic operations. And even further, is it possible that these algorithms will be not just good in theory, but can be effectively realized in practice?
So I can take this question. Certainly it's possible. If you look at the evolution of factoring algorithms, there was very considerable and fast progress between the 70s and the mid-1990s. And then everything froze, more or less. The number field sieve was invented in the first half of the 1990s, and it is still the best algorithm that we can use today. So I can say that the fact that we haven't come up with any new idea in factoring algorithms over the last 25 years is an indication that maybe we've reached certain plateau. Now, this is as far as factoring algorithms is concerned. As far as the size of the key, the recommended size of the key, of course, it's also influenced by Moore's law and the fact that our computers are getting much bigger and can compute more. So the original recommendation for the key size of RSA was somewhere around 350. This was the challenge that we put up in the Scientific American publication, describing RSA, and this was broken a few years later. And then it was recommended to use 512 bits, and this was broken by the number field sieve. And then we switched to 1,000 bit RSA. And then together with a student of mine, Ran Tomer, we showed a wafer scale design of some hypothetical standard device that could break the 1,000 bit RSA. And then everyone switched to 2,000. 2,000 the moment seems secure.
Are these brute force methods that just
No, none of them is brute force. Brute force, already at 100-bit size, you will not be able to do anything.
I think that we have time for 2 more questions. Is that good? Where is the microphone?
There's a hand up right here.
Question right in the center here.
Okay. We have one right here. With,
Maybe you should take off the mask.
Adi just mentioned Moore's law for classical computing. If there isn't a Moore's law for quantum computers, is there any reason to believe that quantum computing will ever be a useful computing device? And another quick question. My understanding is Scott Aronson claims no NP problem can be solved on a quantum computer. Also, my naive understanding is there is no cryptographic scheme that is provable to very encryption of provable NP. And so I'm wondering, are those statements true now, and do you think they will remain true?
So I can answer, but I don't want to dominate the discussion, so maybe you want to answer?
Sure, I can answer and you can check if it matches the answer. So I think it's unlikely that we'll ever have an NP-complete cryptographic scheme. There are some complexity theory results that say that something weird will happen if we have those. And as far as quantum, is there a Moore's law for quantum? This is harder than the question that we were guessing on before, right? 20 years or 30 years. I mean, this is way too early to tell. I have no idea. I think Adi gave me this question on purpose.
No, I doubt that even if Moore's law exists, that unless it continues forever, that it will have much impact. Think about Moore's law on classical crypto systems. So we could easily break, 40-bit keys in the past, and computers became much better. So now we can break 64-bit keys by exhaustive search on, on sufficiently large supercomputers, but not enormously large. And I can guess that the NSA, I have no information, but I can guess that the NSA can solve 2 to the 80. But unless you think that Moore's law will continue for many, many more years, I don't see how you are going to do 2 to the 256 computation on that supercomputer that will result from Moore's law in the future. Moore's law will break down at some point.
Well, it already has in some sense, because for a long time it was based on increasing the clock speed, and we can't do that anymore without melting the chips. So now we have multiple cores. That means you have to have parallel algorithms in order to consume all of the flops that are available.
And another reason why Moore's law was in effect was we kept shrinking the feature size on the chip.
That was what Moore's law was.
Yes, and now we are getting to the point where with the few nanometer technology, you are having transistors with, which are using a few dozen atoms in them. And once we get down to fraction of an atom, we'll have to think otherwise.
But then it's quantum.
Yes.
I mean, Moore's law is actually a law about feature size.
Right.
The more general form, one is the NSA form of it is due to Jim Fraser. The cost of computation drops a factor of 10 every 5 years. Now the question, there are lots of mechanisms by which that could be true, but indeed it's hard to believe it's going to go on forever.
And as long as we're talking about classical computing, if you're interested in that sort of high-performance computing, Dr. Dungar's work is amazing, and just how he benchmarking and defining, and he keeps the top 500 list and so on. So yeah, if you really want to see, we just crossed the exaflop target. I couldn't believe that. An exaflop on a single computer. Okay, down to the last question. Where's the mic right now? So let's go right there, I guess.
It's been waiting for a while.
Yeah, I'm sorry that we couldn't get to everybody. Of course, everybody here, I assume you'll be here for the afternoon, or at least at lunch.
We're here.
So.
We're hungry.
Okay.
Okay, so this might be a stupid question, because as a mathematician I am quite familiar with the field. My brain is conditioned to the n-bit system, and if I have research, there was some numbers, like 52 bits, and all in the decision. And I was just wondering what makes it so that we can have numbers of qubits that are out of the n power on computers.
Would anybody like to take that?
I didn't hear the question.
Oh, the question is about why is it that adding a qubit doubles and I know that's not exactly right, but approximately, why is it that adding a qubit is exponential as opposed to linear?
Why 53?
Yes. Why 53 is another question.
This is related to the topology of where do you put those superconducting elements on the surface of a two-dimensional device. And the numbers that IBM is choosing are also strange. The next generation, which is due in about 2 months, is supposed to have 433 qubits in them. And you ask, why 433? Because that's how you arrange things into clusters and interconnect them in the right way.
Does it have to be a prime number? It sounds like they're all prime numbers.
No.
No, 72 came up here, right?
72 came up. Yeah, we have 53 and 72 were the two that I know about.
These are engineering considerations.
But the problem is that they have to become entangled, and so you have to create a topology in which that's feasible.
Mm-hmm. But can anybody actually answer the question, why does it double with each qubit?
Okay, I can easily answer, but please.
It's the number of states that a qubit can be in. It's in more than 0 and 1. It's not just 2. It's an almost continuous variable in terms of the number of states it can be in.
Okay, thank you.
Maybe I'll just elaborate on it a bit. So you saw earlier in Witt's presentation that the qubit can be in a superposition of a 0 and a 1. 2 qubits can be in a superposition of 4 possible states, 0, 0, 0, 1, 1, 0, and 1, 1. And it can be at the same time in all 4 of those states. Some of them will have a higher probability of being measured, some of them will be a low probability. And then if you go to n qubits, then you just write down all the possible combinations. Now, a regular computer, classical one, is going to be in one of those 2 to the n at any given time. A quantum computer is simultaneously in all of them. That's why the power of classical computers doesn't go up by a factor of 2 when you're adding 1 more bit, because after all, you are in only one of those states. While in quantum computer, you are in all of them, and the number of states is like 2 to the n.
Yeah, that's good.
All right, I think that takes us to the end of the session. Thank you all for your questions and for your interest. Thank you to our president.